how does that work in practice? Now, we've tried this out in a whole range of buildings in the UK, and we hope, obviously, this building here is the School of the Built Environment at Heriot. We tested the product in there first. Basically, you go into the top of the vertical stack, which is, of course, dry. There is no water up here. This is just a vent going through the roof. What you do is you have a 3-port ball valve. Normally, it is in this mode. In other words, the vent stack is completely open as it would be under normal circumstances. Down here, you have an exciter that can, whoops, why isn't that working? There it is. That can put a pressure transient into that pipe, and then, of course, you can motor the valve to let that pressure transient go down the system, and you can take your pressure trace, let it run for a couple of seconds, and you will know whether or not you've got the dry traps. This was a plant room in the roof up here, and one of the traps we obviously checked was a floor trap, because that was very close to what had happened in Amoy Gardens. If you remember from the earlier slide, it was a floor trap that was causing the problem, so we thought we'd start with that and show you that as an example. So what happens is that the ball valve rotates. It's a 6-inch ball valve. The oscillator gives you a pressure wave. That finishes, and the valve rotates back. Now that is real time. That's how long the test takes in that particular building. And what we can see is, down here, that the 2 traces, the stored perfect building trace, this one, diverges from the trace with the dry trap at this point. And again, we know the time, we know the velocity, so we know where the trap is. So in other words, this is a very simple technique for actually identifying a trap seal that has been depleted. Now, of course, I've said it's non-invasive, non-destructive, remote, and of course, you know, if we started off, as Phil Campbell will remember because he was with us early on in this process, by putting in a 30mm pulse. And of course, we decided that that might be somewhat disturbing for somebody who might actually be using one of the facilities when that happened. So we moved to an exciter with a different sinusoidal. Now this is 10 hertz. If you use a pressure transient, which is a sinusoidal pressure transient at 10 hertz, you get about 10 millimeters of oscillation in a trap, which might still be excessive. If, on the other hand, you go to 10 hertz, then probably those at the back won't even realize that water is moving. The disruption of the water is about 1 millimeter in that particular case. So in other words, at 10 hertz, you really do have a non-invasive system because you're not actually, the person is not aware that anything has happened. We've tested this in 4 buildings. This is the one that Phil accompanied us to. It's in Dundee. It's a block of 17-story block of public authority housing, which was due to be destroyed and blown up about 6 weeks after we finished working on it. This has been a very good relationship with Dundee Council because it means that you can make as much mess as you like. You can knock down as many walls as you want. There isn't really a problem. And we did our initial work in this building. We then moved to Heriot, and again, this building is one that we control. So to some extent, you think, well, that's not a really good test because you're in control of the building and goodness knows what you've got up to. This building at the bottom is the Royal Bank of Scotland building. Of course, now following the crash of the banks, we actually own this in the UK. We're very proud of that. We now have 75% of the Royal Bank of Scotland, as I'm sure you do in the States with various your banks. So congratulations to all of us. In this particular building, we had something like 160 traps on that we could actually monitor from one excitation point. So that was a great success. And over here, we have the Royal Infirmary in Edinburgh, where we have looked at a particular vertical stack running through a series of wards and treatment rooms. Now, we see that there are quite a few applications for this technology. Clearly, the healthcare one is a possible, really quite a possible large application of this, but by its very nature, perhaps more difficult to break into because of the regulatory structure around health buildings. My own view is that I'm sure that the first sales of this device will be to high-end apartments, where, you know, on Park Lane or in Manhattan, somebody visits the apartment every 3 months and has got enough money to be concerned about whether or not the traps have dried out and the place smells. So in other words, using this technique, you would be certain that every time you arrived, you were not met with an odor. Of course, this is the world's tallest building in Dubai. I wanted to just show you how long a test would take. And I think that, there we go, 5 seconds. For the world's tallest building at 826 meters or whatever it is, we can do that test in just under 5 seconds. I've had tremendous support on putting together this presentation from Crystal behind these curtains, and if we had this set up in Dubai, then we could have done the test from here. In doing the tests at the Royal Bank of Scotland in Glasgow, we were able to undertake the tests from Edinburgh. Now, I mean, for those of you who know a little bit about Scotland, there's an old joke that says Glasgow is 50 miles and 5 centuries away from Edinburgh. Anyway, no, okay. But we could run this test in Dubai from Ontario on our computer without any problems at all. So in other words, what we've invented is not a device but a business. In other words, you could imagine that you had a call center in Hoboken, and you could be checking buildings as far away as Sydney and Sao Paulo before lunchtime without any problems. I'm very grateful to the Royal Air Force for the photograph, and of course we all recognize the Red Arrows as the world premier aerobatics team. Anyway, the point of this presentation was to try and get home the idea that research partnerships between industry, code authorities, and academia really do work. I mean, I think that we have found out over the last decade that we have been able to interact with industry and produce devices that have actually helped people. I think the first example I gave of the Hong Kong application, we actually went to Hong Kong a couple of years ago and saw this, and it was extremely satisfying to think that something that you had invented had actually improved the quality of people's lives beyond any measure, because there was nothing else was going to be done about that situation apart from the remedial fit. So I think that with the sealed building, we have the ability to now look at very special types of building that we don't need to design in the old way if we don't want to. And with the trap seal detection device, I think we've turned the world on its head, because we, as people concerned about pressure surge and pressure transients, we have always tried to eliminate pressure transients. And of course, in this application, we're using it the other way around. We're using the same theory to actually give us a tool for really protecting people from cross-contamination and the sort of thing that led to the surge, the SARS problem in Hong Kong. And I think that what I feel very strongly is that what we need to make these partnerships work is a mutual understanding. An understanding from academia that industry has problems, and an understanding from industry that you have to have the imagination not to be afraid of the mathematics. I think that's the point. It's not a problem, it's a tool for us to move forward. So anyway, I'd just like to thank you very much for listening to that presentation. It's based on the work of the Drainage Research Group at Heriot and all our partners who've been working together with us to try and improve the public health agenda for the next century. Thank you very much indeed.